This is section 1.2, functions and graphs. Okay, functions are a big deal in mathematics. Once we learn about them, they don't go away. They really are a big deal. So we're going to get to functions in steps. Our first step, Cartesian products. This is the same Cartesian as in Cartesian plane. So, definition. Let A and B be any two sets. The Cartesian product of A and B, and it's noted like this. It looks like you put the time symbol between the two sets, and it's read A cross B, is a set of all ordered pairs. A comma B, where little a is an element of capital A, and little b is an element of capital B. Notice, it's ordered pairs. We've seen ordered pairs before. And notice, since it's an ordered pair, the order that you write it matters. AB is not the same thing as BA. So we have seen ordered pairs before with the plane. Remember, it was also called the Cartesian plane. The Cartesian plane is R cross R. Remember, this R stands for our real numbers. Since this does look like multiplication, R cross R is sometimes read as R2. So, an example. Let's let capital A be the set that contains A, B, C. I'm going to let capital B be the set that contains 1, 2, 3. We're going to find A cross B. Okay, we're going to find A cross B. Now, A consists of numbers and B consists of letters. So, no, other way around. A consists of letters, B consists of numbers. So the ordered pair will be a number followed by a letter. So our solution. In essence, we're finding the plane for these two sets. Okay, that's really what we're doing. So we construct what looks like the X and Y axes upside down. So this is kind of like my horizontal axis, my vertical axis, and I seem to be putting more emphasis on quadrant 4. Now, if we were actually having all numbers, we'd put little tick marks and do 1, 2, 3. We're not going to do that. We're not going to put the little tick marks. Instead, across the top, we're going to put the elements of A. So I'm going to have A, B, C. And then down the vertical axis, we're going to put the elements of B. So 1, 2, 3. Inside of here, inside of what looks like quadrant 4, will be the elements of A cross B. So we now fill in the elements of A cross B. We're going to go across the rows. Remember, the letter comes first. So for the first row, I'll have A1, B1, C1. For the second row, these 1s should change to 2s. So I'll have, for the second row, I'll have A2, B2, C2. And then for the third row, I should have A3, B3, C3. Okay, now these 9 ordered pairs, in essence these 9 points, that's A cross B. That's the plane for these two sets. Okay, that was our first step on the way to functions, the Cartesian product. Remember, Cartesian product lists all possible ordered pairs. Now for us in R cross R, we couldn't list them, we just drew the picture of the Cartesian plane. So our second step on the way to functions, relations. Okay, definition. Let A and B be any two sets. A relation from A into B is any collection of ordered pairs from A cross B. So the Cartesian product, A cross B, lists all possible ordered pairs. A relation takes some of the ordered pairs. So a relation is just a bunch of ordered pairs. That's all it is, just a bunch of ordered pairs. Now we do have some terminology that goes with this. So some terminology, conventions, and facts that go with relations. Number 1. The set of all different first coordinates in a relation is called its domain. Now notice it is a set, so if you're listing a bunch of numbers, you must put them in braces. Number 2, the set of all different second coordinates in a relation is called its range. So again, it is a set, you need braces. So for a relation, its domain and range worry about, not really the sets A and B. Number 3, relations are usually, but not always, named by letters. Now believe it or not, we've actually seen relations before. We just didn't call them relations. So we never really named anything by letters. So this convention we have not yet done. Number 4, all equations define a relation. Remember, to draw our graphs, or to draw our equations, we had to have some ordered pairs. That's what a relation is, a bunch of ordered pairs. So all equations define a relation. However, not all relations have equations. So remember, anytime you write an equation in X and Y, you have a relation. Number 5, all graphs, even if the graph is just a single point, represent relations. So anything you draw on the XY plane is in fact a relation. Number 6, for relations defined by equations, the domain is a set of all different x values. This is because in the ordered pair xy, x is the first coordinate. Now in xy, y is the second coordinate, so for relations defined by equations, the range is a set of all different y values. So again, that's because in xy, y is the second coordinate. So students usually think of domain as x's, ranges as y. Okay, so again, remember, we worry about domain and range. And again, remember, all equations in x and y are relation. Anything you draw on the xy plane is a relation. Let's try some examples to see if we've got the concept of domain and range. So find the domain and range of each relation. Remember, domain and range are sets, so don't forget the correct notation for a set. So here's my first relation. R consists of the ordered pairs 0, 4, negative 3, 2, and 5, 9. Now, if you were to graph this, it is just 3 dots. Don't play connect the dots to make a triangle. It's just 3 separate dots. Now remember, the domain, it's the different first coordinates. So 0, negative 3, 5. And don't forget the braces for a set. Okay, now again, don't use parentheses, don't use brackets, it's braces. For the range, it's the different second coordinates. 4, 2, 9. And that's it. And it's pretty easy. I mean, what could go wrong? Someone pokes your eyes out. Number 2. S consists of the ordered pairs 5, 11, 7, 11, 14, 11. Now again, if you graph it, it's just 3 dots, and don't connect the dots. Remember, domain, different first coordinates. 5, 7, 14. Don't forget the braces. The range is the different second coordinates. 11. Okay, don't list it 3 times. Remember, in a set, don't list the same thing 3 times. With sets, you don't do that. Just list 11. If you list it 3 times, it's not simplified. The domain and range must always contain something. So if you say the domain and range don't contain anything, that they're empty, that can't happen. Let's move on to the big step. Functions. So from here on out, everything we talk about is going to be a function. Definition and terminology. Definition. A function is a relation in which no 2 ordered pairs have the same first coordinates but different second coordinates. So a function is a special type of relation. All functions are relations. So again, no 2 ordered pairs have the same first coordinates but different second coordinates. What does this really mean? If we take the point of view that we will not repeat any ordered pairs, which we're not going to do because that makes it too tricky, the definition is telling us that all of the first coordinates of a function are different. So that's how you tell with ordered pairs whether or not your relation is a function. If all of the first coordinates are different, that's a function. So since a function is a relation, all of the terminology, conventions, and facts about relations apply to functions as well, especially the notion of domain, range, and the fact that we name them by letters. Equations and functions. Now, we already know how to do ordered pairs as functions. All of the first coordinates are different. What about equations? Now, recall that all equations define a relation, all of them. Since some relations are functions, then some equations define functions. Remember, some of the relations are functions. All of the equations are relations. So we sometimes say an equation defines y as a function of x. Okay, we also use that phrase with ordered pairs. So y is a function of x, y is a function, or just the word function, they're all the same. So how can we tell if an equation defines y as a function of x? Okay, there are actually several restrictions. We're just going to look at 2. So number 1, if there are any even powers of y, then the equation does not define y as a function of x. The other restriction that we're going to worry about is if y is inside absolute values, then the equation does not define y as a function of x. Now again, there are a bunch of others, but these are the 2 big ones that we will worry about. So now, why is this the case? This is because y squared and negative y squared give the same result. Like 2 squared and negative 2 being squared, they both give you 4. And absolute value of y and absolute value of negative y give the same result. Absolute value of 2, absolute value of negative 2, they're both 2. So determine whether or not each relation is a function. Here's our first one. R consists of the ordered pairs 5, 6, negative 3, 11, 12, 14, and 3, 10. Now, it is a relation. If you were to graph it, it's 4 dots. Remember, for ordered pairs, all of the first coordinates must be different. And they are. So that is a function. So since all the first coordinates are different, it is, in fact, a function. Number 2. S is the ordered pairs 1, 4, 4, 1, negative 3, 12. Now again, if you graph it, it's 3 dots. And don't play connect the dots to get a triangle. Again, for a function, look at the first coordinates. 1, 4, negative 3. They're all different. It's a function. Number 3. T consists of the ordered pairs 4, 8, 6, 8, 11, 8, negative 12, 8. Okay, now the second coordinate is repeated, but that doesn't matter. For ordered pairs, you look at the first coordinates. Are they all different? Yes. That's a function. Again, if you graph it, it's just 4 dots. Number 4, U consists of the ordered pairs negative 5, 3, 4, 2, negative 5, 11, and 3, 1. Looking at the first coordinates, negative 5 got reused. It's not a function. But remember, it is a relation. Number 5, I have x equals y squared plus 2. Okay, for equations, you look at the y. I have an even power on the y. That's not a function. It's okay to have an even power on x, but not on y. So this is not a function. I've given you a couple of ordered pairs that reuse the same first coordinate. 3, 1 and 3, negative 1 both make that equation true. So it reuses the value of 3 if you're looking at ordered pairs. Okay, number 6. Absolute value of y minus 4 equals 2x minus 4. Again, look at the y. It's inside absolute values. It's okay if x is inside absolute values, but y can't be. This is not a function. And I've given you a couple of ordered pairs. 5, 10, 5, negative 2. They reuse 5. And they both make the equation true. Remember, y cannot have an even value. Y cannot be inside absolute values. Excuse me. Functional notation and evaluating functions. Okay, remember, evaluate means crunch it out to a number. This is not a new way to do math. It's functional notation that you got to get used to. So there's not a new way to add, subtract, multiply, or divide. It's just notation. So let f be a function that squares things. It just goes around squaring stuff. So we have the following ordered pairs for f. I could have 0, 0 squared, which equals 0, 0. I could have 1, 1 squared, which is 1, 1. Remember, f goes around squaring stuff. I could have 2 and 2 squared, which equals 2, 4. I could have negative 6 and negative 6 squared, which would be negative 6 comma 36. Notice, I can't list all the ordered pairs. So in general, I might write something like this. X comma x squared. Remember, f squares things. As an ordered pair, this is supposed to be an x and a y. If I were to write the equation, this would be y equals x squared. Because notice, x squared took the place of y in the ordered pairs. So the equation for this function is y equal x squared. What we want is the functional notation. So the last ordered pair, x comma x squared, gives us a formula for f. Remember, the equation is y equal x squared. So we write it like this. Using functional notation, we write this thing. And it's read, f of x equals x squared, or f at x equals x squared. So the f with the parentheses around the x, that's f of x or f at x. F of x is more common. Now again, remember the formula, or excuse me, the equation would be y equals x squared. The functional notation is f of x equal x squared. So the terminology that goes with this, okay, with this f of x equal x squared. Okay, the f, that's the name of the function. This x inside parentheses next to the f, that's called the argument of the function. It's what the function acts on. It's what the function is going to do something to. And this part to the right of the equal sign, that's the rule or formula for the function. It tells you what to do with the argument. In this specific example, it says square it. So the function always acts upon its argument. Let's try some examples. I'm going to let f of x equals 4x squared minus 6x plus 8. G of x is 3x minus 7, and h of x is 12. Okay, I want to evaluate the following. Simplify your answers. Do not factor. When you're evaluating functions, don't factor. You never factor to evaluate a function. You don't factor your final answers when you evaluate a function. The only times you factor are when the directions specifically say factor. Another time you factor is if you're solving an equation that has an x squared or bigger exponent on x. Then you have to factor and set each factor equals 0. And the third time you would factor is if you're trying to multiply, divide, or simplify a rational expression. Other than that, don't factor. Don't factor any of your answers here, even if they will factor. Now, these three functions will appear for each example we do. Now, each example doesn't use all three functions, though. So here's our first one. Again, here are our three functions. Evaluate f of negative 3. Okay, I'm evaluating a function at a number. So what does this notation mean? This means, in the formula for f, replace x with negative 3. So I'm going to go back up here and replace these two x's with negative 3. So we are actually evaluating the expression 4x squared minus 6x plus 8 for x equal negative 3. If we did not have functions, that's what we would say. Evaluate 4x squared minus 6x plus 8 for x equal negative 3. So we're just going to plug in x is negative 3. So I have 4 times negative 3 squared minus 6 times negative 3 plus 8. So again, I replaced these two x's with negative 3. It's now my dear Aunt Sally problem. Okay, the negative 3 squared will be 9. So I'm going to have 4 times 9, minus times minus is plus. So 4 times 9 plus 18 plus 8. 4 times 9 gives me 36. So 36 plus 18 plus 8. And when you add it all up, you get 62. 62 is your final answer. You don't need to do anything else with it. So a warning here. Excuse me. So warning. Do not write f of x equals 62. That will be marked wrong. It is wrong. Also, do not write x equals 62. That will also be marked wrong because it is wrong. In this example, f of x is 4x squared minus 6x plus 8, and x is negative 3. The number inside the parentheses, that's the x value. This is the functional formula. It is f of negative 3 that is 62. If you were told to write an ordered pair, the ordered pair is negative 3 comma 62. Okay, very seldom do we actually write the ordered pair. Your final answer, the only thing you need to write down is your final answer is just 62. Again, don't write f of x equals 62. I'll mark it wrong. Don't write x equals 62. It's wrong. It's f of negative 3 that's 62. So heed the warning. Our second example, g of negative 3. So in the formula for g, replace x with negative 3. Replace that x with negative 3. So 3 times negative 3 minus 7. I get negative 9 minus 7, which is negative 16. Okay, negative 16 is your final answer. Don't write anything else. Negative 16 is your final answer. Number 3, h of negative 3. So in the formula for h, replace x with negative 3. There is no x. But there is no x in the formula for h. There's only 12. So that means that h will always give back 12, no matter what x is. H is called a constant valued function. A constant valued function always gives back the same value regardless of what you give it. Now, don't say it's going to be 12 times negative 3. In order to be 12 times negative 3, there needs to be an x sitting there, and there isn't. So no matter what you give to h, it's always going to give back 12. So h of negative 3 is 12, because again, 12 is all you see on the right side of the equal sign. There is no operation to do. Number 4, f of 6. And the formula for f, just plug in x is 6. So replace these two x's with 6. So 4 times 6 squared minus 6 times 6 plus 8. Okay, 4 times 6, okay, 6 squared is 36. So 4 times 36 minus 36 plus 8. Okay, 4 times 36 is 144. So 144 minus 36 plus 8. And when you do it all, you get 116. Okay, 116 is your final answer. G of 0. So, in your formula for g, let x be 0. So, I'll have 3 times 0 minus 7. 0 minus 7, which is negative 7. Negative 7 is your final answer. Number 6, h of 33. Remember, there is no x with in the formula for h. Whatever you give h, you're getting back 12. So h of 33, it's 12. Again, there is no x in the formula for h. There's nothing to do. Number 7, f of z. We're evaluating a function at a letter. So this means in the formula for f, replace x with z. So replace these two x's with z's. So I'll have 4z squared minus 6z plus 8. You're done. Don't factor it. Don't set it equal to 0. Leave it alone. Notice it's better to evaluate a function at a letter instead of a number. What if I had g of x plus y? 2 letters. So I'm going to replace this x with x plus y. So I'm going to have 3 times x plus y minus 7. Now I can distribute the 3, but does anything interesting happen? 3x plus 3y minus 7. No, nothing combined. So could we have left it alone up here? Yes. Okay, so notice even if you have 2 letters, there's really nothing to do. But maybe there was something peculiar about g that made it that way. G of x plus g of y. The function appears twice. Okay, g of x is going to be 3x minus 7. G of y, replace the x with y. So there's 3x minus 7. There's my g of x. 3y minus 7, that's g of y. Now, can I leave it alone? No. Negative 7 plus negative 7 is negative 14. You've got to do it. So you got 3x plus 3y minus 14. Okay, this one there was more to do because the function appeared twice. Number 10, f of a plus b. So in your formula for f, replace x with a plus b. So 4 times a plus b squared minus 6 times a plus b plus 8. Now I can distribute the minus 6, and I can square out a plus b. Now if you don't remember how to square a binomial quickly, just do a plus b times a plus b and do FOIL. But remember to square it, square the first term, twice the product, square the last. So I have 4 times a squared plus 2ab plus b squared. I've distributed my minus 6, minus 6a, minus 6b plus 8. So far, no terms have combined. If I distribute the 4, 4a squared plus 8ab plus 4b squared minus 6a minus 6b plus 8. Nothing combined, really, did it? So could we have stopped up here in terms of the function evaluation? Yes. But because of what happens later on, you do need to be able to take it to this final step. You really do, because of what is going to happen to us later on with functions. Remember, we've just learned about functions in this section. So you really do need to be able to go this far. What if I have a letter and a number? Okay, now, my letter and number, I didn't pick the best function since h is a constant valued function. So h of x minus 5, again, there's no x in the formula. I just get back 12 again. Let's try something like that with either f or g. I'm going to do it with g first, since g is not quite as complicated. So I'm going to give a letter and a number to g. I've got g of x minus 2. So replace this x with x minus 2. Remember, that's what that means. Whatever's in parentheses replaces the x in the formula. So 3 times x minus 2 minus 7. Now hopefully you see if we distribute, terms will combine. So if I distribute the 3, I have 3x minus 6 minus 7. And it's the minus 6 minus 7 that combines. I get 3x minus 13. So it looks like if you have a number, even if there's a variable in the argument, you do have to do extra work. Okay, let's try something like that with f. So for number 13, f of a plus 3. In your formula for f, replace the two x's with a plus 3. So I'm going to have 4 times a plus 3 squared, minus 6 times a plus 3, then plus 8. Okay, we need to square the a plus 3 and distribute the minus 6. Now again, if you cannot square the binomial quickly, do a plus 3 times a plus 3 and do FOIL. I'm going to have 4 times a squared plus 6a plus 9. Remember, square the first, keep the sign, twice the product, square the last. Okay, this is distributing the minus 6, minus 6a minus 18, and then plus 8 was still sitting there. Okay, I can go ahead and combine the negative 18 plus 8 while I distribute the 4. So I have 4a squared plus 24a plus 36 minus 6a minus 10. Now again, the minus 10 came from negative 18 plus 8. And see, can I combine something now? Yeah. 24a minus 6a and 36 minus 10. So I have 4a squared plus 18a plus 26. Don't factor. Don't make any attempt to factor. Remember, when you're trying to evaluate a function, you're not factoring. So don't factor it unless, of course, you want me to mark it wrong. Now, functions, we like formulas. So our next topic, domain of a function from its formula. Okay, notice it's just the domain, not the range. Okay, the domain is sometimes called the input values because it's the values that we give the function. The range is called the output values because it's the numbers that the function gives us. So we're trying to figure out what are the good numbers that we can give to the function. So without going to special functions, which we'll do in Chapter 5, there are only 2 problems with domain. We look at the first domain problem in this section, and the second domain problem will be dealt with in section 1.6. So for your Chapter 1 test, you will have both domain problems. The only thing that's going to be missing are the special functions, and that's in Chapter 5. So the first problem with domains, okay, it's something we already know. We are not allowed to have anything equivalent to 0 in the denominator. Remember, no expressions equal to 0 in the denominator. You can't divide by 0. So if there's no variable in the denominator, then the domain is all real numbers. If there is a variable in the denominator, we do the following. So we're about to look at the method for finding the domain when you have a variable in the denominator. So here's your method for finding a domain with a denominator. Step 1. Set the denominator equal to 0 and solve. Now remember, you're not allowed to have anything equal to 0 in the denominator. So you're about to figure out what numbers get excluded from the domain. So step 2, the values found from step 1 are excluded from the domain. So the domain is all real numbers except for the values found in step 1. Now when you write the domain, there are actually several ways to do it, and when you start doing the problems, you need to read directions carefully to figure out what form is your answer supposed to take. Now if it doesn't list a specific form, you're free to do whatever you like in terms of the form. But if it gives you a specific form that you're supposed to write and you don't write it, it is marked wrong. Remember, read and follow directions. Let's try some examples. Let's find the domain of each function. Now in the examples, I'll show you the different ways you can write the final answer for the domain. Here's our first one. F of x equals x squared minus 4x minus 5. Okay, you look for a denominator. Really, you look for a variable in the denominator. I don't even see a denominator. So there are no problems with domain. So our domain is all real numbers. If you're told to write it as an interval, there it is, minus infinity to infinity. Remember, that is interval notation for all real numbers. Now again, this is the reason. There is no denominator to worry about. Okay? No variables in the denominator. So there's nothing to worry about. Let's try number 2. G of x is 3x minus 6 over 5. Okay, even though there is a denominator, there's no variable there. Okay, so 5 can never be made 0, not even for small values of 5. So the domain is still all real numbers, which again we write as minus infinity to infinity. Again, that's because the denominator can never be 0. 5 can never be 0. Number 3, h of x is 4x plus 3 over 2x minus 7. Okay, we now have a variable in the denominator. Okay, we worry about the denominator being 0. Don't worry about the numerator. Later on in this section, we'll figure out what does it mean for the numerator to be 0. So we set the denominator equal to 0. Okay, again, the numerator doesn't matter. Later on, we'll worry about that. So there's nothing wrong with the numerator being 0 equal to 0. So 2x minus 7 equals 0. A very nice equation. Add 7. Divide by 2. So x equals 7 halves is the bad number. So x equals 7 halves makes the denominator equal to 0. We must exclude x equals 7 halves from the domain. So there are several ways to write the domain. There's actually 4 we're going to look at. Okay, so we're about to look at the 4 different ways to write the domain. Remember, you're somehow trying to exclude 7 halves from the domain. Okay, the first way is as a set. So we write the domain is equal to the set of all x such that x does not equal 7 halves. Okay, now in my math lab, if they want you to do this, they'll actually have the braces set up. They'll have the x such that x does not equal, and you just fill in the numbers. And he'll tell you, separate multiple values by commas. There are no multiple values. Another way is as an interval. Now, if you're doing the number line, you start from minus infinity, you work your way up to 7 halves, and then it's a parenthesis, because you don't want to include 7 halves, and then you pick up from 7 halves on to infinity. So the interval is this. Okay, this is a union. This means you're putting together those two intervals. So minus infinity to 7 halves, union 7 halves to infinity. In my math lab, the union symbol will be there on the math palette on the left side of the problem. In D2L, if you're told to write an interval, or if you want to write an interval that has union, just type a capital U. Okay, not a lowercase u, but a capital U. And please, put a space before and after it, make it easier to read. Okay, now another way to write the domain is, oh, and by the way, it is always parentheses. Okay, another way to write it is as an English sentence. So the domain equals all real numbers except for 7 halves. Another way is actually to make the set form actually very, very informal. Because remember, you're trying to convey that x cannot equal 7 halves. And there's about the easiest way to do it. X does not equal 7 halves. Okay, now remember, this is the set form. This is an interval. This is an English sentence. And this is the very informal form. Let's try another one. K of x is 3x plus 8 over x squared minus x minus 2. Okay, there is a variable in the denominator. So set the denominator equal to 0. Again, don't worry about the numerator for domain. So set the denominator equal to 0 and solve. I've got x squared minus x minus 2 equals 0. Got a factor. I've got to use 1 and 2. The bigger number gets the sign of the middle, so the 2 gets the minus. X minus 2, x plus 1 equals 0. So set each factor equal to 0. X minus 2 equals 0, x plus 1 equals 0. I get x is 2 or x is negative 1. So I'm trying to exclude 2 and negative 1 from the domain. Again, if we look at the 4 ways of writing it, as a set, it's the set of all x, such that x does not equal 2, comma, negative 1. Now again, in my math lab, he will have the braces, he will have the set of all x, such that x does not equal, and you just fill in those. Okay? Don't put them in parentheses. It's not an ordered pair. If you want to do the interval notation, going from left to right on the number line, you would actually see minus 2 first. So you go from minus infinity to minus 1, parenthesis, union, minus 1 to 2, parenthesis, union 2 to infinity. Again, it's always the open intervals because remember, you're excluding those two numbers, and the bracket would actually include them. And of course, with the infinities, you always use parentheses. If you want to write the English sentence, domain equals all real numbers except for 2 and negative 1. And then we make that very informal. Now again, most of the time, you'll be asked to do either the set notation or the interval. Let's go to our next topic. Graphs of functions. The vertical line test. Okay, consider this graph. Looks like a funny looking S. Okay, now it is a relation. Remember, anything you draw on the xy plane is in fact a relation. I don't have any scales on the axes, but I do know on the y-axis x is 0. So I'm going to have the same thing on smaller. This I call the point 0, y1. Okay, the 1 should be closer to the y. It's the first y value, that's why I call it y1. I don't know what it is because I have no scales. But I knew the x value is 0. I'm on the y-axis. Right here, I've got another place where x is 0. I'm going to call that 0, comma y2. I've just reused x equals 0. This is not a function. And I've got one more place where x is 0. Call that 0, y3. This is not a function. Notice if I draw a vertical line right here, I'm going to hit the graph in 3 points. On the same vertical line, they're the same distance away from the y-axis. They have the same x value. So the value x equals 0 was used 3 times. So our graph is not a function. Remember, it is a relation, it's just not a function. In fact, anytime 2 points are on the same vertical line, they will have the same x-coordinate. Remember, the x-coordinate tells you how far away you are from the y-axis. So this leads to the vertical line test. And this is what it says. If a vertical line can intersect a graph in more than 1 point, then the graph does not represent a function. So if a vertical line can intersect a graph in more than 1 point, the graph does not represent a function. Remember, it is a relation, it's just not a function. If a graph is a function, we say that the graph has passed the vertical line test. So passing the vertical line test means you're a function. If a graph is not a function, we say that the graph has failed the vertical line test. So failing the vertical line test means not a function. And remember, our example failed the vertical line test since it was not a function. Let's try some examples. So, some examples. Determine whether or not each graph represents a function. You're just going to write function or not function. Okay, so function or non-function. There are 4 examples. I have the basic circle, the basic line, the basic parabola, and the basic scribble. Okay, for our circle, I actually see a vertical line that hits the graph in more than 1 point. It's not a function. Remember, it is a relation, but it's not a function. Okay, my line. No matter where I draw a vertical line, it only hits it at 1 point. So, it is a function. It's called a linear function. The only type of line that will fail the vertical line test is a vertical line. So all non-vertical lines are functions. They're called linear functions. Okay, our run-of-the-mill parabola. It passes, so it's a function. Your basic scribble. Well, the y-axis hit this guy in a bunch of places, so this is not a function. Okay, let's look at graphing functions. Okay, we're going to graph some functions. Okay, now, we always graph y equals f of x. So the table of values will have headings x and f of x. We plot the points x, comma, f of x. So the functional values play the role of y when you plot points. Since a function is always solved for y, because remember, f of x plays the role of y, your graphing calculator can graph the function. So, some examples, let's graph each of the following. There's my first one. F of x equals 4x minus 5. Okay, if we give it to our calculator, okay, we'll turn it back on, I guess. Okay, do your y equals. You're looking at 4x minus 5. 4x minus 5, and then just say graph. Remember, in D2L, it would be multiple choice, so you look for one that kind of matches that. If we were stuck doing this by hand, remember, it is a line. No variables in the denominator, variables of exponents of 1, and because y is over here already, you can't have an xy term. So, it's a line. All they need is 2 points. We make our table of values. Remember, you're free to pick values for x. Pick super easy values for x. I always start with x being 0. I'll have 4 times 0 minus 5. That's 0 minus 5, which is negative 5. I plot the point 0, negative 5. So 0, negative 5 should be right there. Another easy value for x, 1. So I have 4 times 1 minus 5, which is 4 minus 5, which is negative 1. So I plot 1, negative 1. Okay, 1, negative 1. And now we draw the line. So does this look like what Mr. Calculator drew? Yes, it does. Number 2. I have g of x is x squared minus 1. Okay, I've got a variable being squared, that's a parabola. If we give it to the calculator, okay, give it to the calculator. Let's clear that out. Go to y equal. Let's clear that one out. I've got x squared minus 1. Graph. Okay, there's our parabola. Okay, if we do it by hand. So again, I've got a parabola. Let's plot some points. Again, I will start with x being 0. Okay, pick easy numbers. I've never understood why people go to like 4 or 5. Pick easy numbers. So if x is 0, I've got 0 squared minus 1, which is 0 minus 1, which is equal to negative 1. So I plot 0, negative 1 right there. Another easy value, 1. So I have 1 squared minus 1, which is equal to 1 minus 1, which is 0. I found an x-intercept, didn't I? So 1, 0, right there. Okay, you should pick some negatives. Keep them easy. Negative 1. I'll have negative 1 squared minus 1. Okay, negative 1 squared is 1, so 1 minus 1, I get 0. Another x-intercept. So negative 1, 0. Right there. Okay, hopefully you see the parabola taking shape. But, you know, just for the fun of large numbers, let's do the 2's. So if x is 2, we'll have 2 squared minus 1, which is 4 minus 1, which equals 3. So 2, 3, right there. And for the sake of completeness, let's do negative 2. So we'll have negative 2 squared minus 1, 4 minus 1, which is 3. So negative 2, 3, right there. And now you draw your parabola. And does this look like what the calculator drew for us? Mm-hmm. Number 3, h of x is 4. I have my constant valued function. Remember, no matter what we give the function, it's giving us back 4. This is also a line, though, because there is no variable to worry about. So it satisfies the condition for a line in a rather silly way. But remember, no matter what we give the function, it gives back 4. So if I start with 0, h of 0 is going to be 4. So all the function values are going to be 4. So I got 0, 4. So put my dot. If I pick 1, okay, I get 1, 4. If I pick negative 1, I get negative 1, 4. Horizontal line. A constant valued function graphs as a horizontal line. Okay, let's do the reverse of that. We give you a graph and then ask you to identify some points from it. So function values from a graph. Okay, function values from a graph. This is the reverse of making a table of values. Okay, we will need a relatively accurate graph because you're actually trying to read the points off the graph, which means it's got to be relatively nice. So using the graph of y equals f of x, which is going to be in the next slide, find the following values: f of negative 3, f of 0, f of 4. So the graph is going to be drawn on the next slide. Remember, we're looking for f of negative 3, f of 0, f of 4. Remember, for functional notation, these values in the parentheses, those are x values. Okay, we're looking for the y values that go with those x values. So here's my function. It starts here at the point negative 5, 0, and then it's a straight line segment up to on the y-axis to 2.5 looks like. Then make a horizontal line segment from 2.5 on the y again out to where x is 2, and then pick up from there and go make this line. Looks like the only good point there is right here. What is that? 4, 5. Okay, and then it just goes on forever. So there's our function. Okay, we're going to be asked to read some points from it. Remember, we're looking for f of negative 3, f of 0, and f of 4. Okay, same picture, only smaller. So for x equal negative 3, remember that's what that is. Here's x equal negative 3. Go up and hit the graph. Okay, now remember, you're looking for the y value there. So the technical name is project. So if we project this onto the y-axis, it looks like y is 1. So again, you're trying to read off the y value at this point. So again, it does look like the point negative 3, 1. At least that's what it looks like to me. So f of negative 3 is 1. You can now see why you need a fairly accurate graph. Otherwise, it would be very, very hard to read that point. Okay, number 2 was f of 0. So at x equals 0, remember, that's going to be on the y-axis. Go up and hit the graph. Okay, and then you're looking for the y value there. I'm already on the y-axis. Remember, the y value there looked like 2.5. So f of 0 is 2.5. Okay, and then number 3 was f of 4. So here's x equal 4. Go up and hit the graph and read off the y value there. Looks like 5. Okay, looks like 5 to me. So f of 4 is equal to 5. So this is just your ability to read a graph, and your graph has to be fairly decent, otherwise it's going to be very, very hard to read. Let's take this idea of reading the graph to domain and range. So domain and range from a graph. So we're going to try to get whole intervals. Okay, that's what it's going to amount to. We're going to try to get whole intervals, or maybe a collection of numbers. So for domain, the idea is to project onto the x-axis. Remember, domain, those are the x values. For range, the idea is project onto the y-axis, where the range are the y values. So let's try some examples here. It does not matter whether or not the graph is a function or just relation. Remember, we still project onto the x-axis for domain, y-axis for range. Because remember, we first saw domain and range back with relations. Remember, all functions are relations. So now our examples. Find the domain and range of each relation. Okay, domain and range. Okay, here's my first one. This is kind of funny looking W. Okay, it starts off at this point, -5, 3, and the dot is filled in. So then I have this straight line segment going down to 0, -2. And then from there, go up to the point 2, 1. And then go down to 4, -3. Then go up to 5, 3. So there's my function. It doesn't go on forever. Okay, now here's the idea. Because there aren't any holes, breaks, or gaps in it, I want to go from left to right to find the domain. So I'm looking for the x value that's to the furthest left, right here. The x value is -5. And because the dot is filled in, I will put a bracket for the interval. If it were open, I would put a parenthesis. Now, to find out where does it end, go to the point that's furthest to the right on the graph, right here. That's 5. And again, the dot is solid, so it's a bracket. So the domain is the closed interval from -5 to 5. So for the domain, go from smallest x to largest x. Go from left to right. For the range, you want to go from smallest y to largest y. Remember, in interval notation, smaller number on the left. So that means in terms of the graph, go from the lowest point to the highest point. Go from bottom to top. Okay, looking at our graph, this is the lowest point. The y value there is -3. And again, it is part of the graph. There isn't a hole there. Okay? And then what is the tallest value? There's the tallest value. The y value there is 3. So the range is the closed interval from -3 to 3. So again, for domain, go from left to right. For range, go from bottom to top. Let's try another one. I've got just the straight line segment. Okay, this is an open dot. This one is filled in. That's the point -2, 5. This is the point 3, 5. Okay, for domain, if I go from left to right, the furthest point to the left is -2. The open dot says parenthesis. The point that's furthest to the right is 3. It's filled in. That says bracket. So the domain is left half open from -2 to 3. Okay, the range. Notice the range, there is no up or down. There is just this one y value. Because, horizontal line segment, there's only one y value. When there's just individual numbers for a domain or a range, you use the braces, not parentheses, not brackets. All I'm getting out for the range, the only y value I get out is the single number 5. So I put 5 inside of braces, not parentheses, not brackets, it's braces. So again, if you get individual values instead of intervals, you use braces and separate the individual values by commas. Let's try another one. A parabola. Okay, this point is 0, -4. My y-intercepts are -2, 0, and 2, 0. Now, the parabola keeps going up, 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 and spreading further to the left, further to the right. So if I try to find the domain, remember, this keeps going up and moving further to the left. There is no point furthest to the left, so it goes from -infinity. And notice the same thing happens on the right. There is no furthest point to the right, because this keeps going toward the right. So the domain is all real numbers, -infinity to infinity. If I go from bottom to top, there is a lowest value. Y is -4. It is part of the graph, so I'm going to have a bracket at -4, and it keeps going up, 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 so it goes to infinity. So -4 to infinity with a bracket at the -4. Remember, the infinities always have parentheses. Let's move on to another topic. Zeros of a function. Okay, zeros of a function. Definition. Let f be a function. The number x equals z is called a zero of f if and only if f of z equals 0. Notice, a zero is a number. It's not an ordered pair. It's a number. So a 0 of a function is a number which, when plugged into the function, makes the function equal to 0. Okay? It makes the function equal to 0. You don't evaluate the function at 0, but the number makes the function equal to 0. Let's try some examples. Let's find all the zeros of each function. Simplify your answers. Do not use mixed and resonance answers. If you look at these directions, except for that first sentence, these are my standard directions for solving an equation. Finding zeros and solving equations are basically the same thing. Here's my first example. F of x equals 3x minus 12. Remember, I want to find out where this is 0. I have 3x minus 12 equals 0. I'm solving an equation. Now again, remember, f of x played the role of y with functions. I've replaced y with 0. This is the same thing you would do to find the x-intercepts. So this is the same procedure for finding an x-intercept. So finding an x-intercept, finding the zeros, and solving an equation amount to the same thing. Now, add 12 to both sides. Divide by 3. You get x is 4. The 0 is x equal 4. Don't put any decorations around it. It's the number 4. So finding the zeros, finding the x-intercepts, it's the same thing. Number 2, g of x is x squared minus 6x minus 7. Okay, again, find out where it's 0. So I've got x squared minus 6x minus 7 equals 0. Okay, I got a factor. To get 7, I got to use 1 and 7. To get a minus in the middle, I got to have the minus 7. So x minus 7, x plus 1 equals 0. Set each factor equal to 0. X minus 7 equals 0 or x plus 1 equals 0. I get 7 or negative 1. My zeros are 7 and negative 1. Okay, remember, the zeros are numbers. It's the x-intercepts that are ordered pairs. Remember, finding the zeros, finding the x-intercepts, it's the same procedure. Number 3, I've got h of x is 2x plus 5 over 3x minus 4. Remember, with domain, we looked at the denominator. For a fraction, the only way the fraction is going to be equal to 0 is if the numerator is 0 and the denominator isn't. So finding where the numerator is 0, that's finding the zeros, which is the same thing as finding the x-intercepts. So set the numerator, 2x plus 5, equal to 0. Subtract 5, divide by 2. So my 0 is negative 5 halves. So x equal negative 5 halves is your 0. Remember, where the numerator is 0, those are the zeros of the function. That's also the x-coordinates of the x-intercepts. Worrying about the denominator equal to 0, that's a domain problem. Now, these last 3 functions we just looked at, they're also going to be used in this last topic for section 1.2. So, y-intercepts of a function. Okay, y-intercept of a function. We just really looked at zeros and x-intercepts, same procedure. So, recall, to find y-intercepts, we let x equal 0 and solve for y. That gave you the y-coordinates of the y-intercepts. Remember, you're letting x equal 0. What does this mean in terms of functions? So for functions, this amounts to evaluate f of 0. So to find the y-intercept of any function, evaluate f of 0. Finding zeros is a function evaluation. If you recall back when we were graphing, I always started with x equals 0. We were actually finding the y-intercepts. Okay, so for my examples, I'm going to have the exact same 3 functions that I did for the zeros. So note, a function can have at most y-intercept. Remember, vertical line test. So if 0 is not part of the domain of the function, then the function will not have a y-intercept. Okay, the classic example of that type of function is f of x equals 1 over x. Okay, so f of x equals 1 over x. It doesn't have a y-intercept. It turns out it doesn't have an x-intercept either. So find the y-intercept of each function. Express your answer as a point. So again, I'm going to have the same 3 functions. So we're looking for the y-intercept. So there's my first one. F of x equals 3x minus 12. Okay, remember, to find the y-intercept, evaluate f of 0. So 3 times 0 minus 12, I get negative 12. As an ordered pair, as a point, 0 comma negative 12. Number 2, I've got g of x is x squared minus 6x minus 7. Again, evaluate the function at x equals 0. G of 0. So 0 squared minus 6 times 0 minus 7. You get negative 7. As a point, as an ordered pair, 0, negative 7. Okay, number 3 was that fraction one. So number 3, h of x is 2x plus 5 over 3x minus 4. Okay, evaluate at x equals 0. So h of 0. 2 times 0 plus 5 over 3 times 0 minus 4. So I get 5 over negative 4. Okay, with the minus sign, it doesn't matter if you leave it in the denominator, put it in front of the fraction, put it in the numerator, your choice. As an ordered pair, 0, comma, negative 5/4. So remember to find y-intercept, evaluate the function at x equals 0, do f of 0. That's the end of section 1.2.